So let us continue with this. So we did some example of varieties which had this notion of orientation. And this was required for us to show the existence of these realizing the driving effect as the critical difference. Okay, so now we had this theorem. Let me suggest that at least remind you of the theorem. Last theorem we did was basically so we have this theorem that this is a reminder that f the right Artan stack, drive Artan stack, is with and shifted with unshifted symplectic form. Omega is based on two forms of this stack in the dx. Unshifted symplectic form that X and O compact. We describe what these meant. O compact derived stack. O compact derived stack with a stack equipped with an orientation. We call this an O orientation. We denoted it by the cycle notation, which was a map from CMSA to K minus C. And so this one was actually this Artan complex, and I showed you an example when a variety has an orientation. Okay, of degree D, then assume that the derived mapping the stack all map from X, which is derived the stack F, is itself an Artan stack locally of finite presentation, then over this field K, underlying field K, then the derived mapping the stack from X to F is carries a canonical n minus d shifted symplectic stack. So this was the theorem that we proved. Okay, and then you know that if you have this shifted n minus d symplectic structure, then you can use Joyce's Darboux theorem and write down your stack. is what we did last time, and then I showed you an example of the stacks with a choice of orientation of given degree. And so now some corollaries. So corollary of theorem. Corollary of theorem. This is, for instance, Lagrangian intersections. Lagrangian intersections. It's a derive the stack F and a shifted symplectic form on F. Okay, let F from X to F be a morphism of derived Artan stacks. Okay, we have morphism of derived Artan stacks. Then we have the pullback morphism. Pullback closed to form induced by the pullback morphism, which is pullback of the form, which lands inside this component of closed two forms on X on degree n. Okay, so fine. Now I need to define something. So you're pulling back these things, and you would like to identify them homotopically with each other. So here's the definition. An isotropic structure on F relative to omega is a path between O and F star of omega. Okay, where in this space of closed two forms of degree n on X. Okay, this is what is called an isotropic structure. The space of isotropic structures on F relative to omega is defined to be the path space which is isotropic structures of F with respect to omega, and it's defined as pathes between O and P star of omega inside here. The path. So what is a Lagrangian structure? You see, think about it this way. If you have the Lagrangian, then holomorphic symplectic form in manifold theory. If you have a Lagrangian submanifold, holomorphic symplectic form vanishes on it. Right? This is the homotopical version of that. You have the symplectic form on a derived stack, and you pull it back to some stack, and you would like, in some sense, for the pullback to be trivial. But everything is homotopic, so there's a path between it and the trivial function on X. Okay, so this is the derived version of that very statement. So a Lagrangian is a structure on the morphism F will be an isotropic structure satisfying some non-degeneracy conditions. So this is what it means, a stack being the Lagrangian which has another stack. And what is the non-degeneracy condition? So if an isotropic structure H in the space of isotropic structures on this map with respect to omega, the space of all path is between Q back of omega and O in the space of closed corbs. Consider the two form which is defined as a map from T dot of F, which T dot of F to the structure sheaf of F to N. We know that ambient stack F has a symplectic two form of degree N, so this is by assumption underlying, so this is the underlying the symplectic form on ambient stack F, and its pullback to X, which induces a morphism from pullback of the tangent complex of F to 2 times itself to OX of N. Okay? This by definition now, by definition, H gives a homotopy. Gives a homotopy between O and the composite morphism. T dot of X itself. T dot of pullback of this thing to OX. Right? I mean, I think it is obvious to you that pullback of the cotangent complex of F gets mapped to the cotangent complex of X. Dualize it, then cotangent complex of X gets mapped to pullback of, tangent complex gets mapped to tangent complex of X. So this is natural. And the isotropic structure also induces a composite morphism T dot of F, T dot of X, T dot of x, T dot of x, T dot of f, f, sorry, f upper star, T dot of f to OX of f. So I'm completing this thing on the left. And how is that obtained? Since so remember that this is actually induced by the following, induced by this thing. Yes. So you see. So first, this one, these two, obviously there is a map from here to here, so there is a map from here to here. And then for these two, there is a map this way, T dot of ftx. So if you wedge this with T dot of x, you will get a map from T dot of x. This is the relative tangent complex. So, and hence, which induces a, so this is all in the space, this is in the space maps, space of maps of quasi-coherent sheaves on this drive to stack X to, from T dot of F tensor with T dot of X to OX shifted by N. If you look at this composite morphism, then you will get that the composition of morphisms from here to there gives you a point in this mapping space. Composite morphism lives in the space here. Okay. And in fact, we get a loop. In fact, we get a loop in this space, in this mapping the space, centered at 0. Remember that pullback of your symplectic form, or centered at O. Pullback of the symplectic form is going to be homotopically equivalent to O. So you get a map from O to itself, which in that, such that in that space is a loop centered at O. Okay. So this loop defines an element in here. So in the space of loops, on the mapping space of quasi-coherent maps in the derived category of this stack from T dot of f tensor T dot of x to OX of n centered at 0, which is basically yeah, I think this doesn't match. Okay. Now, by adjunction, we get a morphism theta for H. All of this is depending on this choice of isotropic structure H. As soon as you know that you have a map from omega to omega to O, you will get the loop around O, which is a pointed loop in that mapping instance. Okay, so everything is depending on the choice of isotropic structure. So by adjunction, we get also a map from P dot of X to L dot of X shifted by n minus 1. Does it make sense? Of course it makes sense. Why? Because it's a loop, so 1 goes to here, gets shifted by minus 1, and then this one you dualize it, you tensor it with O. Okay? So, this is by adjunction. And, okay, so if someone asks you, what do you think of this thing? You will see that this is very similar to being the Lagrangian, which depends on H. So now definition, based on this construction, I can define, so let f from x to f be a morphism of derived Artan stacks and omega and n shifted symplectic form on F, an isotropic structure H on F is a Lagrangian structure. Lagrangian structure on F, of course, relative to choice of a symplectic form of given B on F, on ambient F, if induced morphism, which I just constructed there, theta of H from the relative tangent complex of this map F to cotangent complex of X shifted by n minus 1 is equal to SMO. Okay, so this is the definition of a Lagrangian in a derived stack. In fact, this is really so nice, and you can look at several examples of moduli space of coherent sheaves, for instance. Sometimes you actually realize sometimes the moduli spaces are in this derived categorical sense or a stacky sense is a Lagrangian inside some other moduli. You can actually investigate these things in practice. So, I'm trying to say it's so concrete actually. If you expand the definitions and expand the definitions, then you can see that these are actually very concrete. Okay. So this is what the Lagrangian structure is. Now we know that the choice of this isotropic structure. So we know that what is it? So ingredients are symplectic form on ambient stack. We need to pull it back if it falls in the path, in the component that parameterizes path is from that pullback form to O. So roughly speaking, homotopically speaking, it is trivial. And then you have this construction for that choice of the path or isotropic structure. Well, you can get a morphism, and if the morphism is quite isomorphism, it's Lagrangian. So that is it. Now, there's a theorem. Let y to f, x to f be two morphisms, so f and g, be a diagram of derived Artan stacks omega is a symplectic form on f of good degree n, an n-shifted symplectic form, and h and wait a minute. So h and g be Lagrangian structures on F and G. Lagrangian structures. So these define Lagrangian structures. Then the derived, so I have two Lagrangians, then the derived stack x homotopy product over f with y, fiber product, is equipped with a canonical n-1 shifted n-1 shifted symplectic structure called the residue of omega, and denoted by this residue of omega. Actually, you know, the shifted symplectic structures, give me a second. So we have two maps, and for each one I need to fix a choice of isotropic structure, a path. So let's say our maps are F and G, and I pick two isotropic structures, which are Lagrangian structures, H and K, on F and G. This is why I wrote it wrongly in my note, but this is correct. So H and K are those choice of paths in the path space in here after pulling back the omega. Okay. So now I can say that the residue is depending on omega and the choice of isotropic structures on H, F and G. So H and K. Okay, so that's the residue. Okay, good. Okay. So how do we see this? So maybe a sketch of the proof is the following. So you have these two. So you have x going to f, y going to f and g, and you have the fiber product, homotopy fiber product over here. We can call that z. Now each one of these isotropic structures, H and K, give us paths, right? So H and K define, so H defines a path from O to pullback of omega, and K defines a path from O to pullback of omega. Okay. Then this residue thing belongs to pi 1 of space of closed two forms of Z and N, because now we are actually seeing both of these things up. Okay, another mistake. So let us call these things on. Should I? So actually I need to pull back further, right? So P and Q. Each one of these things give me a path, and the path is space in here and here, but I would like to define the residue. I would like to define a shifted symplectic form or a structure on the fiber product. So I have the isotropic structures, but I would like to view them over here. So I call these maps P and Q, so now it's better. Okay. So this now gives me something inside here, which is the same as the connected component of A to closed forms Z shifted by n minus 1. And E from Z to X to F, and Q from Z to Y to F come equipped with homotopy. So you see, now I have a situation where after pulling back to here, I have two paths between pullback of the symplectic form and O, and the paths need to be homotopical to each other. Before I only had one path. So equipped with homotopy, let's write it as U from P to Q. And U star gives a homotopy. Q star, Q star, closed, all of it. Now by concatenation, of H and pullback of omega via this U and K inverse, we get a loop at O in this is space of closed two forms on Z. See that this residue actually becomes a point in the pi 1 of A2 closed forms Zn, which is I0. It's okay. Anyways, I mean, the point is that you have Lagrangians, and for each one of the maps, you have these isotropic structures, which define Lagrangian structures. You pull back, and over here you have a map to O, and over here you have a map to O. Now you pull back both of these two paths into the path space in here, in the space of closed two forms on Z. Now you have these two paths, and you get a homotopy between them. You call the homotopy U, and via the homotopy, by concatenation composing H and U star and the inverse, you will get a loop in here. And that's why it defines for you an n minus 1 shifted symplectic structure. Then we need to show that the underlying, which I'm not going to prove, the underlying two form for this closed form, underlying form for this closed two form is non-degenerate. You need to show this too. You're not done. Now you have, you know that in this space, you have at least one point defined by these two Lagrangian structures, but then you need to show that, yeah, underlying two form of that closed form that you got in here is a non-degenerate two form, inducing with quasi-isomorphism of degree n minus 1 on this. For that, you can look at the proof of PTVD, which is really much nicer than what I wrote on the black.
Sorry, what is the path?
In the pathing space, the morphism.
Path is a morphism from what to what?
Up to homotopy, from the pullback of omega to O.
I mean, a path in the space of form, or what is a path?
It's, I mean, it's like in the mapping space, for instance, mapping the space over a, for instance, space, category of complexes on a variety. What is the mapping between two complexes? It's a morphism between two complexes.
Well, what's a domain? What's a domain?
The domain of this thing is the pullback of the form.
I mean, a path. My intuition is a map from the interval to something. So what is the interval?
Let's see. We would like to define it that way. Okay. You really want to define it similar to the usual topology. It's a,
Understandable.
yeah. So, so let me see. Can we do this? I don't know.
You can do both. You can either think about this as a path in that way, that just an element of the one path put together. This difference in parametrize, and you have
That's what I'm actually thinking.
This is kind of
Explicit parameterization of the path. That's what I'm thinking.
this is standard thing. If you take any simplification here, if it's not a stacked simplification, a simplification set, then you have the geometric realization essentially linear things, and then any kind of simplification element of the simplification set becomes a path between the boundaries. But usually people don't think about it
Yeah.
in terms of paths.
In principle, you can actually do this everywhere. I mean,
It's a combinatorial. So instead of thinking about paths, we think about combinatorial.
if you have map between morphism between two complexes, right? And then you can have a homotopy of morphisms. You can also ask what is the path? What is it, the meaning of path? In some naive way, you can probably parameterize that.
It's not naive, so much naive as it is a geometric realization.
Yeah.
It is very artificial.
Yeah.
So what's a
It's a combinatorial replacement of the interval. So instead of if you think about the interval, it's in terms of simplicial sets, for example, it's a simplicial set that has 2 points.
2 points, and it's a one simplex, basically.
No, it's two. Yeah, it's one exactly. It's 2 points in dimension 0 and one non-integrated point in dimension 1.
Yeah. So it's a map from that to.
If you want to
It's a naive morphism, still I say, because it's a map from whatever you have times that simplicial object that associates each vertex of that simplicial one, that one simplex to each one of your morphisms. Basically, this point of the one simplex goes to one morphism, the other one goes to the other morphism, and the one simplex in between defines the map between the two morphisms.
H and K are both path.
Yeah.
What's a start point?
What is the what?
It starts from O or
O2. Yeah.
What is O?
O is just a trivial.
I mean zero.
Trivial, yeah. 0. Trivial form. Trivial form. I mean, it's a good question.
It's a question of habits, actually.
Yeah.
Once you get used to combinatorial
Yeah,
realization,
exactly.
you get
Okay. So there are some corollaries to this theorem. I mentioned those for you. So here's the first corollary. That x via smooth DM stack and omega a symplectic form on x, and L and L prime in x, two smooth closed Lagrangians. Two smooth closed Lagrangian subsets. Then the derived fiber product L homotopy product with L prime over X carries a canonical minus 1 shifted symplectic structure. Corollary 2, 1, 2, let X be a smooth PM stack, and f and o of x, a global function on x, global function on x, then the differential df from x to cotangent bundle of x, then the derived critical locus of f, which is called the R critical locus. R critical. This is what we described before. The R critical locus is defined as x fiber product over the tangent bundle of x with itself, and this fiber product is with respect to the zero section map and the df. Okay. So there is that. And there is this. And we are looking at, this is the R critical locus of f. Okay. Of the zero section, with the zero of the zero section, the section of df inside the cotangent stack of x carries a canonical -1 shifted symplectic structure. It's a smooth thing, so x is a smooth. Okay, so this is essentially really important. This is where a lot of enumerative geometry lives. If x is a smooth, then the critical locus of this function, which actually takes x into its cotangent bundle, has a -1 shifted symplectic structure.
It depends on the degree of f.
Okay. It also depends on the degree.
So that what you said is correct.
It's 0. This is 0 degree. This is of course global.
It doesn't say degree 0. It can be any section.
Well, degree 0. Degree 0. Yeah, you're right.
But if you choose a non-zero degree, it will be also true.
Also true, but it
will
will
have
be
another shape.
another shape. In that case, the function, you're right, but this actually we discussed this before. Remember that when we were discussing critical loci, we looked at situations where f was a graded potential on your graph. So it was a function but it was not sitting in the degree 0 algebra of your underlying derived. Then you will have a further shift if it is a graded piece. That is a great thing. Some non-trivial piece of the underlying DG algebra of that. Okay, so these are two corollaries. Okay. So let me see how much time do I have. Okay, so I have almost more than half an hour of time. So now let us discuss something else. So let us talk a little bit about two-shifted symplectic. We will come back to this Lagrangian intersections, but now let's talk about two-shifted symplectic structures on the moduli space on the category of perfect complexes. Perfect complexes. Perfect complexes or the moduli space of perfect complexes. Moduli is better. Okay.
So we minus
Minus two shifted. No. Two shifted. Just two shifted. It will be just two shifted for them. But then when I give you, this is the category of perfect complexes. Then I'm looking at, I will pull back some of these perfect complexes to a variety of given dimension. And that induces a shifted symplectic structure on the moduli space of perfect complexes on that variety. For instance, if the variety is dimension 3, then it will be 2 minus 3. If it is Calabi-Yau 3, for instance, it will be minus 1 shifted. If it is Calabi-Yau 4, it will be minus 2 shifted. But this one is just all of the perfect complexes. This is a ginormous category. Okay? So this has 2 shifted symplectic structure. Okay, so the functor our perf sends a DG non-positively graded algebra A to the nerve of the category of perfect ADG modules. On R curve, there exists a universal perfect complex. Let's call that an E, and the DG algebra over R curve is given as the endomorphism algebra of this universal complex. So some perfect complex E, and then which is in the derived category of quasi-coherent sheaves, on the R perf itself. R perf is a functor, but it's represented by a stack. And so it has a universal object too. And okay, so now, and then we have a DG algebra over this stack, which is basically endomorphism. R home. I call it E dot. E dot. This is the one that gives you the DG structure on the R curve. Okay. The derived loop stack derived loop stack of R curve, which by definition, like before, was the space of derived space of maps, R map from circle to the ambient stack. The derived loop stack, which gets mapped to. We discussed this thing. I gave you a variety. I looked at the loop stack of that variety, and then we used the HKR isomorphism to show that via this map to push forward the structure sheaf of the loop stack in here for our variety recovers the Durham algebra of our variety. Now we are replacing the variety with this stack of perfect complex, ginormous thing. Okay? So this is the loop stack for that, and the derived loop stack is identifiable with derived loop stack of invertible loop stack over R curve of invertible elements of this endomorphism algebra A of A. R endomorphism of E dot. So basically, all our curve derived loop stack of our curve is something I would like. I mean, these people PTVV call it a upper star, and that is the invertible elements inside here. Things with circle automorphism. So U1 automorphism. So those are the invertible elements. It's really nice and beautiful. So since A is a perfect DG algebra, we see that this is essentially what we are doing in our project. We see that A upper star as a derived Artan stack, Artan group stack. Artan group stack over our curve, and the quasi-coherent coherent DG algebra, DG algebra, DG algebra over R perf is A itself. So this actually tells us that we have a natural quasi-isomorphism from the tangent stack or tangent bundle of our curve to R on CE1, which by definition is A shifted by 1. But we have seen this before. In the case of a variety, we saw that the loop stack can be the shifted tangent bundle, so this is the same thing. After using the HKR, we are pushing forward the structure shift of the loop stack, and our variety would recover the Durham algebra. And that is the derived tangent complex, and then this is the dual. So we get a morphism from the push forward to the. So this is exactly same as what we have discussed so far, except here the underlying algebra is recovering endomorphism of your complexes, together with the with their internal break in the structure.
Sorry, I didn't see where the shift comes from. Where the shift
It is the same thing as the shifted tangent bundle that we had before. Remember that I realized the derived loop stack as the odd affine line. So if you really want to figure it out, go back to that derived. But we also had a discussion about this thing. I actually remember that this was one of the things actually I was myself confused about, and I wrote some explanation of it. Why should be the shift?
What's a projection map from A star to R perf?
From the loop stack?
Yeah, explicitly using A star.
Yeah.
What's a map from A
This
star?
is the one produced similar to the HKR, honestly. I mean, that is actually the
Yeah,
theorem,
can
right?
you write down this map?
So this one was this one, right?
Yeah.
So this one was what? So this one was x tensored x times itself, okay, over its diagonal. So what do you do? So you have this thing. You can do it for also, but you have this thing, diagonal embedding of x inside x times x, and then you look at the fiber product over here. This was the loop stack.
Yeah, I mean,
So that's the projection.
I mean, explicitly for A star.
Explicitly,
You just put A is attached to
yeah.
something, you forget where it was
Yeah, that's
attached,
right.
and just remember the map. So you forget the complex of which A is not automorphism, you have to map from A to the stack. And now you have the map, you have the A. Forget the A, that's the map.
Let me see. So no, but it's easier than that, right?
What I said is the easiest. It's just No, this is what I just.
But think of this as the R curve now.
So
You can just realize the projection map as the morphism of the algebra.
yeah, I think his question is how do you get from A to the R curve? But A is that.
Forget the map from the circle.
Yeah. Exactly.
Forget the map from the
Forget
circle.
full map.
Yeah, that's right. Yeah, that's right. This is also the map from the lupus space, right? This is also the lupus space of this thing.
But if you want to have it explicitly, if you have a G ring, G ring B, then a B point in this R curve would be map of set B into that stack, which means that it's just given by copies of B modules. And A will be the automorphism of this perfect copies of B modules. So how do you go from A to B? Just forget it.
Forget the automatic.
That A, and you remain only with the map from set B to the R curve.
Also.
So it is as simple.
Or realize it as the corresponding algebra map from here to here. Or, if you like, realize it as this one. This is also good. This parameterizes also, you know, invertible elements in this endomorphism algebra. And you're forgetting those automorphisms given by GL1 of the algebra.
Forget everything.
Forget everything.
Exactly.
Land on the underlying algebra. Which also actually, this morphism is telling you the same thing. Yeah, and you have many ways of seeing it. Okay. So you have this now, this identification. Identification can be used to define a two-form. Define a two-form of degree 2 on R curve. How? Well, just tensor this thing with itself. You have tangent complex. Okay, and it becomes symmetric second product of A shifted by 2. And you can map that to O of R curve via, which is by trace, so which is basically given by this composite map. So you have this map, multiplication A times A, so this is the one. This is you want to land on O, so this is where this is. Then you go to A, and then you go to trace by taking the trace, which I explained to you last time, to O of the graph. Okay. And the trace, we know what it is. A is itself endomorphism algebra complex, and you're taking the trace of that thing. And you have land on functions, global functions on R. Now, yeah, so just remember that this thing is the same as this. This 2-form is non-degenerate. This 2-form is non-degenerate, and it will be non-degenerate, and it will be the underlying underlying two form of a canonical shifted symplectic structure on R. Again, remember that when I compute when we obtain the two form, the symplectic form is basically an infinite sequence. So this is just a T0 truncation of it. And the idea is that this two form that we defined in here, this non-degenerate two form, is the underlying T0 part of the symplectic structure on R. Okay? Okay. Now, so let us talk a little bit about that thing. So symplectic form on our curve. Well, now we know that it's going to have an underlying T-form given this way. Consider two derived stacks. One of them is the stack of negative cyclic complexes or homologies, which is taking you from derived affine, opposite category of derived affine stacks over the field to simplicial sets. The other one is HC, which is taking you from also simplicial affine, opposite category of affine things to simplicial sets, and I need to define for you what these things are. So these are cyclic complexes and the negative cyclic homology, negative cyclic complexes, which we had defined before. And so let me tell you as functors what these do, and then so the derived stack NC is obtained from the functor that sends a KDG algebra A to its simplicial set obtained by the complex negative cyclic complex of Durham complex associated to A. Remember that this we had before. We know what this is. This is the sum over all P of omega lambda. P of omega A shifted by P. So this is the one that sends this to the underlying simplicial set of that complex. The other one, the derived stack HC, sends an affine derived scheme, let's call it X, to the global functions on the Looper stack of X, which are homotopy, S1 homotopy invariant. So this is the space of S1 homotopy fixed functions these are where this is the one that spits out for you closed forms on X. Because those are S1 homotopic invariant or S1 homotopic fixed functions on the loop step. And in fact, to have commutative, e.g. algebra K, the commutative K dg algebra, let's say A, we can assign the corresponding commutative simplicial K algebra. Let's call it A prime if you like. A prime, and consider S1 tensor over A over K with A prime, which is another simplicial algebra, another simplicial commutative algebra, on which the simplicial group S1, which we realized before as BZ, acts. Then the space of homotopy fixed points of this action is a model for HC in negative of spectrum of A. So it's a functor. It takes you a derived affine scheme to S1 invariant homotopy S1 invariant functions on the loop space of that affine scheme. So this says actually that if you pick the affine scheme, how do you construct this space? Look at the underlying algebra and construct this simplicial algebra, and then there's an action by S1 on it, and then you can discuss what is the fixed point of that action. And the fixed point of the action of S1 on these is model for image of this.
So is that tensor product also the loop space?
Oh, yeah, I mean, it's the algebra of the loop space. Yes. Just write down the mapping space from S1 to X, and then you get a map in the level of algebras and put the other one. Use a junction, and you will get that out. Okay, so this is that. So basically, all we are saying is that this is the S1 tensor with A prime over K. Fixed homotopy fixed with respect to actions. Okay. Now a theorem Cohen and Vetsozi says that this drive the stack NC and AC negatives are equivalent. Okay, and hence the Chern character map from, so I define it as the map from R perf to AC invert, AC negative of the universal complex. The universal complex is going to be in I0. These two things are equivalent, and hence the Chern character map induces a Chern character map from R perf to this space of negative cyclic complexes, and that actually shows you that this guy, image of the universal complex, is going to be in the component of mapping the space from R perf to NC, which is the same as H0 of negative cyclic complex of this one. Negative cyclic complex of this means negative cyclic complex of the Durham algebra of R perf. We have defined these notions before. Whenever I put the space in here, I mean really the Durham complex of this. And this is actually an important theorem. Actually, now I will show you why this is called the Chern character map, but in the proof. Let me show you. It's almost, it's almost obvious. These are cohomologies, and we are realizing them inside. They're homological of these things. So here is in fact, we can project Chern of E dot onto the degree 2 part, degree 2 piece. So we have this Chern of E dot in the degree 2, which sits inside here, negative cyclic complex of R perf of degree 2, and that is the I0, the connective component inside this space of closed 2 form on R perf of degree 2. We had a discussion on how we are realizing all of these symplectic formulas, cohomology classes. We are using that in here. So here's a theorem. Main theorem, P2BP, the closed 2 form Chern of E dot in degree 2 is a shifted symplectic structure on R perf. the proof. You need to show that why is it the closed, I mean, the way that you get the closed 2 form is almost obvious, but you need to show that the underlying 2 form of this closed symplectic 2 form is the one I defined for you before. So you need to produce that form from here. Okay, so here is the proof. So you start with the perfect, okay, so the perfect complex E dot on X. Let's okay, so let's see. Let us start with a perfect complex E on X. So let's say this is a derived Artan stack. Later X for us will be the R perf. Okay? And then its churn character. Churn of E. E is now a perfect complex on some derived Artan stack. Has image in Hodge homology of X. So you can write down churn character of E as the sum of the pieces, all the churn numbers, the churn characters of different degree on E, which belongs to summing over all P, HP of X, lambda P, L dot of X. True. Yes. Think about their homology. And induced by natural morphism of negative cyclic complex to Durham complex. Okay. These Hodge homology classes can be written in terms of a tier class of this perfect complex E. A tier class of a perfect complex is an element of this group. A tier class of some complex E is an element of this group. This is interesting for geometers. Often in geometry, you will have a vector bundle and you would like to define a connection on that bundle. You might not always be able to do so. A tier class is a point in a space of obstructions to defining this connection on the bundle. This is the space of obstructions to defining the connection on the bundle. And a tier class is a point of this space. Okay? And same thing can be extended to objects in the derived category. If you want to define a notion of a connection on an object in the derived category, then the connection is basically this thing. Okay. This is the tier class of E. And so, which we can compose with itself. So I have only 2 more minutes, so sorry for going over time. You can compose this with itself, and you will get, you can see that you can have a map from E to E tensor of dot of x shifted by 1 to E tensor L dot. So you take this thing and you tensor it again with this guy. Second Wish product of L dot of x shifted by 2, and you can keep going like that. So we get composition of the ideal classes, which are given as morphisms from E to E tensor with ith Wish product of lambda of x shifted by I. Okay? And now, which we can write as, which we can write as a map. So ideal class, this I-fold product of ideal classes of E can be written as a map from O of x to E dual tensor with E tensor with ith wedge product of L dot of x shifted by I. I'm just putting this E on this side. But this is beautiful because E dual tensor E is underlying algebra. And the morphism algebra that we want. Right? So we get this, now composing this with the trace. We obtain classes in HI of x and I shifted ith exterior product of L dot of x. In fact, we have churn 1 of E, churn I of E is equal to the trace of this I-fold product of a ideal class divided by I factorial, which lives inside here. This is how, from a complex, you can actually get these elements of cohomology, Hodge cohomology, elements in the Hodge cohomology of X. Now for X equal to R curve, the cotangent complex L dot of X shifted by 1 is naturally equivalent to, well, the tangent complex of R curve was A shifted by 1. So the cotangent complex is the dual. And A was E dual times E. And the morphism algebra. So this is equivalent to E dual times E dual, because the tangent one is this guy, and that is the E tensor with E dual. E dual tensor with E tensor. And the idea class is a map from E to E tensor, the cotangent complex shifted by 1, but I'm going to replace it with this one. Really beautiful. Simplifies things big time. Which is adjoint of multiplication E tensor A to E. Because what I can do is, this is A, and this is dual of A. And so I can put the A on the other side. From here, we get the formula turn 2 of E, 1 over 2 trace of multiplication, which is inside H2 of R first. Okay, so this is actually the proof. It actually shows you that when you start from the symplectic form, its underlying 2 form is exactly the one that you obtained via second symmetric product of A and then taking the trace. So basically, this is that. Okay, so this finishes this part. Next time, I will cover for you some corollaries of this. Okay, and then we mentioned. So let me see. So we have some examples in here. There's of course interesting thing about -1 shifted symplectic structures. Now, when you have a variety, this is a two shifted symplectic structure on R perf. Now you will have R perf on a given variety, and based on the dimension of the variety, this shifted symplectic structure can induce symplectic structures of this degree, 2 minus t, and this is going to be the dimension of the underlying variety. So the most interesting ones are the threefolds, Calabi-Yau threefolds, which have -1 shifted symplectic structures. So you immediately actually see that the moduli space of coherent sheaves on the Calabi-Yau threefold has -1 shifted symplectic structures, and then also by previous discussions, it can be written as a derived critical locus of a function. That is beautiful. And then we will do fourfolds, which has -2 shifted symplectic structures. But that is supposedly supposed to be written as the derived critical locus of a graded function. It's just that the function doesn't live in the zero part of the algebra. Okay, graded potential. And then next time I will also show you how nicely all of this construction tells you that as soon as you have a -1 shifted symplectic structure on a moduli space, that moduli space will have, on a derived moduli space, the underlying, so if you have M, and the underlying truncation of M, this is a derived moduli set. If M has -1 shifted symplectic structures, you can pull it back to the homotopical zero truncation of the moduli set. This is the honest moduli set. And it induces, first of all, a deformation obstruction theory. Not only that, that deformation obstruction theory will be symmetric in the sense of Behrend and Fontaine. So all of this business of doing derived differential geometry and derived algebraic geometry actually recovers the constructions that we have in algebraic geometry. Okay, any questions? All right. And then later we will move to maybe fourfolds.